All right, so here's where we deviate a little bit from alkene chemistry. So we're doing alkynes still, right? And we're going to do oxidation, and we're going to do a similar reaction. This is mercury and sulfuric acid and mercury sulfate, right? And so remember, this was a Markovnikov addition. This was a Markovnikov addition, and that means that the hydroxyl is going to go on the inside, right? But here's where it's different. It's different because this is actually not nearly as stable as this. And so what happens is this goes through a process called tautomer. These are tautomers. Tautomerization. Okay? They're tautomers one of another. And it turns out since this is much more stable, this is what happens. So this is an acidic solution, right? We make the hydroxyl here, and then boom, this is what we find in the end. Here's how it happens. It happens, there's my tautomers. It happens by, well, you know what? I wish I could give you a chance. I could force you to try this because if you had enough time and a couple blank sheets of paper and a pencil, you could figure some of this out. Look at, I've told you before that the pi bonds are nucleophilic, right? And since they're nucleophilic, they're like basic. This is just the same mechanism we had for addition of water across a double bond. The first step anyways. This is just a proton transfer, right? So we get these nucleophilic pi bonds come over and they're basic because they're nucleophilic, right? And so we get a proton transfer. This is an acid-base reaction. Now, this is the intermediate, right? And since this is the intermediate, there's a carbocation right here. Well, this carbocation says, wait, you have a lone pair of electrons over there. Why don't you share? And so it is resonance stabilized. So it turns out they do share, all right? Now, it shares. This is a resonance structure. Now, of course, the plus is more comfortable on the carbon than the oxygen, right? So this is the dominant structure of that hybrid. But enough of this exists such that another water molecule can come over and say, hey, I'll take your proton, and you can have all the electrons, right? And it goes off as H3O+. So there we are. And then we end up with a ketone, which is much more stable than an enol. I didn't say that. Here it is right here. A ketone is much more stable than an enol. And so even though this is sort of an uphill process, right? But as all reactions, you have some kind of an uphill process before you get a downhill process, right? And sure enough, that's good because it's favored by thermodynamics. So if we want to do an anti-Markovnikov addition, right? Which is regioselectivity, right? We want to do anti. We do it the same way as we did it with alkenes. We do it with a borane THF, complex. Man, my vocabulary. I'm really sorry. A borane THF complex, and then we follow it up with hydrogen peroxide and sodium hydroxide, and we get the anti-Markovnikov addition. Okay, this is tautomerized by base, right? Which we'll see in a second. We'll go through this mechanism in just a second. Matter of fact, we'll do that now. We'll do this next slide, okay? So this is going to be base catalyzed. So here's your enol, right? Which is a similar structure we had before. Here's your enol. And you can see that this is going to be the most basic, the most acidic proton, right? So your base comes over here, bam, bam. Then you have 3 lone pairs of electrons on there, right? And you get this is called an enolate anion, right? These electrons come down here, make a double bond. You see those? They're right here. And these electrons come up here, and can you see them? They're right here. Okay. And so this is obviously the more stable of the two because it has a negative charge on a electronegative element. However, since this is such a downhill process, the water molecule donates a proton to this very super basic carbon, right? And boom, we get the aldehyde. Okay? So my recommendation is you get a blank sheet of paper and walk yourself through both the acid catalyzed tautomerization and the base catalyzed tautomerization. And I think you'll just be practicing things you've done before, and it'll solidify other things as well as get you comfortable with this material. Now it turns out if we use borane, that we oftentimes are going to get two successive additions, right? So you'll not just get the borane that goes in there, you'll get another one that goes into the other double bond, right? And so you're going to get something that you don't want. So in order to prevent that, we can take some kind of a dialkyl borane, which only has one hydrogen on it, right? And since it only has one hydrogen on it, it's greatly restricted, and it's also bulky. And if it only has one hydrogen on it, we can get to a high yield of an aldehyde from a terminal alkyne. All right. So here's the example: it's diisoamyl. That's supposed to be no. Diisoamyl borane. Diisoamyl borane. Right. It's supposed to be an O, isn't it? I think that's supposed to be an O right there. Okay. Anyway, pardon me. Pardon the timer. All right. So let's go back to that slide. Wait, where are we? Sorry about that. All right. Let's go back here. Diisoamyl borane, and so this is just like a BH3 THF complex, except it only has one hydrogen on it. It's got two alkyl groups on it. That's the point of that. Okay, so in summary, where are we here? In summary, we for a terminal alkyne, it's got to be terminal, of course, right? Because it has to be terminal. So for a terminal alkyne, you can get Markovnikov hydration, and you get a ketone in the end, right? So this looks familiar. When we did that before, we were making an alcohol with an alkene, but the enol gets tautomerized to a ketone, and the same thing here. You get an intermediate of an alcohol, but this gets tautomerized to an aldehyde. All right, so write those mechanisms out. Write the mechanisms out, but you also should write out the reactions on 3x5 cards and have those memorized soon. They're super powerful reactions. You can see I can take an alkyne and I can get a ketone, or I can take an alkyne and I can get an aldehyde. All right, good luck.